At 11.86, the voltage drop across this component is 2.76. This time it is in linear conduction mode. Assalamu alaikum wa rahmatullahi wa barakatuhu. Friends, welcome back to my channel. In this session we are discussing TL431, very special and critical component in switching power supplies. We will try to understand its function and its use, how it works. It is available in different package styles. This is 431, this 431AIH, and most commonly used this TO92 package. It looks like a transistor, but it is not transistor. It is named Adjustable Reference Regulator. If we see its symbol, it is very closer to zener regulator, zener diode. Cathode, anode. But here is a third pin, that is reference pin. It is pin number 1, cathode pin number 3, anode pin number 2. As zener is connected in circuit, anode is connected to ground side, cathode is connected to positive supply. Zener works in a reverse bias region. In zener region, same to zener, it works as a regulator, but its working style is same to zener, but its internal structure is different. Cathode, anode, reference. If we see its block diagram, equivalent circuit, this is reference pin, this is cathode, this is anode. But when we see, there is no zener diode inside. Here is a transistor. Collector is connected to cathode pin, emitter is connected to anode pin. Base of this transistor is being controlled by a operational amplifier or comparator. Inverting pin is connected to 2.5 volt reference, that is built in to this component. Reference, anode, cathode, 1, 2, 3. This is pin number 1. This is pin number 3. This is pin number 2. When we apply slightly higher voltage to this reference voltage, there will be a difference. That time it will turn on this transistor, it will drive the base. When base current will flow, it will allow collector current. And if we see its some equivalent circuit diagram, reference pin is here, then this is output side. Emitter is connected to anode, collector is connected to cathode. We can say this is C pin, collector pin, and this is E pin, and here we have base. That base will work at a specific voltage level that is built in reference in this circuit. When we say there is a transistor, that means we have some limitation of the voltage. Collector to emitter voltage, VCEO, because when transistor is off, all the voltage will drop across this transistor. For example, we provide 100 volt here. When it is off, all the 100 voltage will appear at these 2 points. Off transistor behaves like open circuit. That means VCEO. In this TL431, that are 37 volt maximum. Voltage between these 2 points, absolute maximum voltage 37, allowed voltage 36 volt. So 36 volt can be applied maximum to this circuit. When it will off, it will block the voltage. When it is on, at that time, in this situation, it will drop approximately 1.4 volt. But here, because there is built-in circuit, so it will drop approximately equivalent voltage to V reference. That is 2.5 volt. That means when it will turn on, when it will conduct, it will drop 2.5 volt here, and remaining voltage will be applied to the load, to the next circuit. Recommended operating voltage 36 volt. When we will connect any load in this circuit, what is the capability of this transistor? That is maximum 100 milliampere. Minimum 1 milliampere cathode current. Maximum 100 milliampere and minimum 1 milliampere. From 1 milliampere to 100 milliampere current can be obtained from this output transistor. How much current it will take for turning on? That is reference current at this pin. Maximum 1.8 microampere. That means it is negligible current. 1.8 microampere current here. Minimum cathode current, that is the extreme minimum current for regulation, that is 0.5 milliampere. Let's say we will assume 1 milliampere. So we will drive any load between 1 milliampere to 100 milliampere. To operate this component, we need 2.5 volt at this pin, reference pin. Then it will turn on its transistor. We can say it is a voltage detector IC with 37 volt or 36 volt here. It needs 2.5 volt at this pin, reference pin. When 2.5 volt will present here, it will turn on this transistor. When this transistor will on, anything connected at collector pin, that will turn on. Just for example, if I want to make a feedback circuit for 12 volt power supply, this is the return path, and I want to place this component to sense the voltage, we need voltage divider network. When 2.5 volt reference will be provided to this component, it will act. To make a voltage divider network, we need some amount of current. Let's suppose I will make this voltage divider at 1 milliampere. That's nice. 12 volt. What is the RT? Total resistance. V over I. 12 volt divided by 0.001. 12 divided by 0.001, it is 12K. And how much voltage we need here? 2.5 volt between these 2 points. For that purpose we need resistor value of this resistor. Let's suppose this is R1, R2. We need 2.5 volt. The current value is 1 milliampere. 2500 ohms. 2.5K. Remaining voltage here, 12 minus 2.5, 9.5. What is the resistor value? 9.5 volt divided by 0.001, 9.5K. This is R2. R1 is 9.5K. So it is difficult to find 9.5K. We will select 10 kilo ohm. If we will select 10K, that means more voltage will drop here. We need to readjust the value of this resistor. Now we selected 10K, 10 divided by 9.5K, that is the calculated value. It is 1.05. We will multiply this value with this resistor to bring new value. It is 2.631. R2 new 2.631K. So these are now values. Although we will not find 2.631K, we will use any resistor available 2.2K, and we will use a trim pot variable resistor to make it exact 2.631K, or we can select the next higher value 2.7K that is available in market. When we will use these two values, 10 plus 2.631, 12.63K, 12 volt divided by 12.63, the amount of current will 0.95. That's excellent. That is not increasing. That is marginally closer to this value. That's good. We will inject this voltage to the pin number 1 of this reference regulator, and this is pin number 2. Pin number 2, anode pin, will be connected to ground. When it will receive 2.5 volts, it will turn on this transistor. When it will turn on this transistor, that time there is zener impedance, that is cathode to anode impedance, that is also to be calculated. But most of the time VKA, voltage dropped across cathode to anode between these 2 points, are very closer to V reference. We can say when it will turn on, when we will provide 2.5 volt, that time it will drop 2.5 volt between these 2 points. When it is off, when these voltage are less than 2.5 volt, all the supply voltage will drop across this junction, these 2 points. But when 2.5 volt are present, that time it will hold just only 2.5 volt, and remaining voltage will be transferred to the load. For example, I want to turn on this LED. Its standard current is 10 milliampere, and I want to turn on at mid level 7 milliampere, 8 milliampere. We can obtain current 1 milliampere to 100 milliampere from this output transistor. I want to turn on this LED. We have supply voltage here now. If we are using same supply, that time we need a resistor here. Why? Because from this point to this point 12 volt minus 2.5 volt, that will drop across this component, minus 2.5 minus LED voltage, LED junction voltage, normally 1.8 volt, depending on the color, minus, I will consider 1.8 volt, because if I will test it using multimeter, red LED, it is 1.773. I will consider 1.8 volt. 12 volt power supply, 2.5 volt for this component, 1.8 volt for this component, remaining 7.7 volt. We need a resistor to drop this voltage. Our current limit, V over I, 7.7. Let's suppose I want to turn on this component at 7 milliampere. 7.7 divided by 0.007. It is 1100 ohms. It is best to take 1000 ohms standard resistance. If I will use 7.7 volt and divided by 1000, it will 7.7 milliampere. So it will within range, because maximum 10 milliampere, 15 milliampere current can be provided to this LED. So it will 8 milliampere, that's good. 9.91K, this resistor good. It is 2.158. We need 2.631K, 20K. So I will use just only one potentiometer. I will not use this resistor. I will use just only these 2 points, the last 2 points. So it is now 2.6K. Now this potentiometer is working as a resistor. Common point, this resistor and this potentiometer will go to reference pin. As I discussed here, we need 1K resistor here with this LED. When we will connect 1K, that time here approximately 7.7 milliampere current will flow in this path. Now we have two currents, one here, the second 1.8 microampere current maximum here, reference current. It will not make a big loading effect on this voltage divider, because here is approximately 950 microamperes. So 1 microampere, 1.8 microampere will not make a big deal. So current will flow here, that is load current, that is LED current. Cathode of this LED will go to TL431. In case we are using optocoupler, at that time it will drive optocoupler. And I will use 1K resistor as a current limit resistor to drop the extra voltage 987. That is 1K with tolerance. Let's apply voltage. I will apply variable voltage. I will use this multimeter to see the input voltage. DC voltage, and here we will monitor the reference voltage, that is pin number 1 on this multimeter. Both multimeters common will go to power supply common. Power supply common. Input voltage, reference voltage. Now I will apply power. When we have 2.8 volt, just only 0.6 volt is on reference pin, this yellow wire. I will increase the voltage now. .9 volt, the LED is off. At 6.6 volt, 6.8 volt, we have 1.5 volt reference. Still it is not allowing any current. A minor current will flow for reference regulation for its internal circuit. At 10.7 volt, the reference voltage are 2.25. There is no cathode current. This is leakage current that is required for the internal chip. 2.39, 2.415, 2.46, 2.485. The LED is full bright. This time it received its required current. Now our load is turned on. If we are driving any optocoupler, this time the optocoupler will turn on its internal IR and it will turn on the output transistor. If the voltage will drop from here 11.86, because this time these resistors are not exactly accurate. This is slightly less, so this is the reason it is triggering before 12 volt. Let's see voltage drop across this transistor. At 11.86, the voltage drop across this component is 2.76. This time it is in linear conduction mode. The output transistor is in linear conduction mode. Any ripple here in input, it will increase or decrease the voltage of this junction. We can see the saturation voltage approximately 1.9 volt. When the reference voltage are less than 2.49, 485, 49, 2.5, that time maximum voltage will drop across this component. Maximum voltage minus 2.5 volt reference 9.87 out of 11.79, 9.87 that are dropped here. By controlling the reference voltage, it will control the cathode current, that is output current. I hope this video is informative for you. If it is good, give a thumb up. If you have any question, please write in the comments. Thanks for watching. Assalamu alaikum wa rahmatullahi wa barakatuh.